Hi, my name's Jan Zika. Welcome to Higher Theory and Applications of Differential Equations. This is just a short video to introduce myself and the course, let you know what's going to happen over the next 10 weeks. This is a fantastic course. I love teaching this course. I'm really disappointed from my own point of view that I can't meet you all. I can't give lectures. I love presenting all of this information to you face to face. But on the other side, I think for you, for all the students out there, I think this online format is actually going to work really well, if not better. And it was something that I've had in mind for the last few years of whether this course could be sort of flipped. And some of the activities that we've developed over the last few years are actually quite well suited to an online format. So don't worry, I think this course is going to work really well for you online. And I just wanted to introduce myself on this video and tell you a little bit about the course, a few pretty pictures, and give you a bit of an idea of what you can expect. Okay, I'm just going to share a little PowerPoint presentation here. So as I said, this is Higher Theory and Applications of Differential Equations. This is just a part 0. So these aren't the formal lecture notes. This is just an introduction. So what I'm going to do here, this whole course is about solving differential equations, understanding differential equations, understanding whether solution exists to differential equations, and giving you some of the foundation methods for just dealing with differential equations. Differential equations basically describe all of nature, everything we see around us. So they're extremely useful, extremely broadly applicable. And just in the next few slides, I'm going to give you an idea of a tiny subset of systems that these types of equations can help you to solve. Okay, so early in the course, the first thing we're going to discuss is linear systems. And one of the really interesting things about linear systems is that different solutions can superimpose on one another. Okay, now I think that might not be obvious to you as I said it then, but if you think about the natural world, if you think about things like waves, so I'm just going to show you now an animation it's a simulation, but it could very well be satellite images of a tsunami generated in 2014 off the coast of Chile. Okay, and this is a very similar effect that you would see if you threw a rock into a pond. You would see waves being generated and emanating from the point that the rock landed. But as those waves collided with, say, a boundary, with the side of a pond, and were reflected back, the waves would superimpose. You would get crests and troughs, and they would be superimposed on top of one another to create these beautiful wave patterns. So that's basically constructive negative interference, just superimposing of different solutions to a differential equations on top of one another. That is not just a fascinating thing about differential equations, it's something we're actually going to exploit throughout the course to solve different problems. Okay, so in the second part of the course, we're going to discuss dynamical systems of differential equations. Now, I can assure you that no wolves or sheep were hurt in the process of making this animation. But this is a classic system of differential equations called the predator-prey system. And oh, we've got a bit of sound here, do we? I better turn that off. But what you can do is you can simulate the interaction of different processes, and it can be linear systems, but it can also be nonlinear systems. So we'll touch on some nonlinear systems. This particular one discusses the interaction between a predator, which in this case is a pack of wolves, and a prey, which is in this case are some sheep. Now, what you can see happening here is the wolves have eaten lots of the sheep and they've gone hungry. So then the wolves have died off and the sheep that were remaining have been left to procreate. And what we can do, this is a numerical simulation, but actually mathematically, we're going to solve systems of equations that describe things like sheep as one equation, wolves as another equation, and then we're going to let those equations interact in a system of differential equations. And as you can see here, it can simulate all sorts of different processes. Okay, I'm going to move on. So after the dynamical systems part of the course, we're going to go to a little bit about boundary value problems. And then we're going to start thinking about generalized Fourier series. And underlying the idea of generalized Fourier series is the idea of eigenfunctions and eigensolutions to problems. So this is about the same problem with many different solutions that are all correct, but just have different characteristics, okay? A bit like eigenvalues of a matrix. We can have eigenfunctions, different functions that satisfy a certain solution, okay? So this particular case I'm going to show you is a set of solutions to the simple problem of the beating of a drum. So a drum is an elastic membrane, and it has boundary conditions. It's fixed at its boundary, and it obeys a kind of a wave equation. And what we can do is, depending on how we hit a drum, we will generate different solutions, different waves. And here we're going through them, and it's a two-dimensional problem, so there are many different flavors or shapes of these waves, and they have different frequencies. And as I was talking about before, the idea of superimposition is going to become important. And what we can actually do is we can describe any sound we get from a drum, no matter how we hit it, with the sum of all of these different eigensolutions with different weights. So we're going to think about series to solutions to the very complicated problems. We're going to break it down into simple problems and then add up all the solutions. And we're going to generate some pretty pictures like this. So finally, I just wanted to show you a kind of application that we'll get to the end of the course. So this is actually a real simulation I'm going to show you now. Sorry, a real, this is a real physical process being videotaped here effectively. And this is the kind of system that our differential equations will be able to simulate. So we're going to talk about something called the heat equation or the diffusion equation. And this is actually a diffusive system being generated through turbulence in a channel. So it's actually a kind of a fluid dynamics problem. But what's fascinating about this is that we can write down with pen and paper or with iPad or tablet and stylus, we can write down the equations that broadly dictate the behavior of these sorts of systems. So this particular experiment involves basically a fast fluid flow with a small amount of tracer, of dye being injected into the flow on one boundary. So it's basically, you can think about this as a two-dimensional problem with boundary conditions at the top, boundary conditions at the bottom, and a kind of a material that's being diffused through the system with time. All of that we'll be able to describe with differential equations by hand. Interestingly, if you wanted to simulate all of these fine details that we see in these different actual physical experiments, the processes, the mathematics that we will describe in this course are actually the underpinning mathematics for a lot of those numerical methods. So it's really underpins a whole range of areas of applied maths. Okay, I'm just going to finish the pretty pictures there, just give you an idea of the course structure. So the course is split into 5 parts: linear ODEs, dynamical systems, initial boundary value problems in 1D, generalized Fourier series, and initial boundary value problems in 2D and 3D. Okay, every bit of the course is going to build on every other bit, which I think is a really nice thing about how this course works. Even in the last week, you'll still be thinking back to things that you learned in the first week and making use of them. Okay, every fortnight, I'm going to release videos and lecture notes, which you'll be free to go through at your leisure. There'll be live sessions on Thursdays at 1 p.m, which is one of the original lecture times. where I'll make some announcements and we'll have some interaction, maybe go through a few different examples, discuss the lecture notes, some of the theory. In the tutorials, we'll have a formal tutorial session. We'll go through a set of the tutorial problems, but you all should come and ask questions and we should interact. And then there'll be consultation time starting in week 2 on Wednesdays at 10 a.m. And depending on how people interact with these different sessions, I'm willing to adapt. So if you have any thoughts or advice, hopefully you only do this course once. So if you want it to be better, you should say sooner rather than later. Okay, so lastly, I just wanted to talk about the assessments, which is something that everybody is always very interested in. Okay, so what we're going to do is we're going to run something called a workshop. In the workshop, you'll write some formal written answers to some problems, and the first draft of those will be due in week 3, the middle of week 3, actually 9 a.m. on Wednesday of week 3. So very, very soon. So you're going to have to get through those lecture notes, think about the tutorial problems, and have a crack at the workshop problems very soon. I'm going to put out the workshop problems on Wednesday and make an announcement, and we're going to talk about them in the first interactive session on Thursday. There's going to be some peer review involved, and there'll be more details on that. And in the final versions will be due again Wednesday morning of week 5. So we've got an early assessment. It's just worth 10% of your mark. And I expect everybody to actually put in a lot of effort for that and produce a very good, I want everybody to do well in the workshop, is what I'm saying. So the test will be in week 7. So week 6, which is the sort of the slow week, as it were, I won't give you any new material, and will basically be an opportunity for you to do revision. So that'll be 9 a.m. Wednesday, week 7. Then there'll be another workshop at the end of the term, which will be worth another 10%, and then there'll be a final exam. So good luck. Stay in touch. Come along to the live sessions, the tutorials, interact on the forums, interact with each other, and I'm going to be available for the next 10 weeks, and I really look forward to working with you all. Thanks very much.